In this chapter, I'm going to talk about how temperature affects the rate of a reaction. So most reactions occur faster at higher temperatures. And here are a couple of examples that are probably quite familiar to you. So food cooking faster, salt dissolving faster, and metabolism running faster. So we're going to be talking about how temperature affects the rate of a reaction, and we're also going to look at a couple of other factors that affect the rate. We've already looked at concentration, we'll look at that briefly again, but there's a couple other factors that we're going to be considering in this section. All right, like I said, concentration, we've looked at that before, so that has to do with the number of particles or molecules that are in the solution or in the gas phase or wherever they might be. And the more reactants there are, the more possible collisions that can occur. And because more collisions can occur, that will affect the rate of the reaction, increasing it if there are more collisions. But the other consideration we have to look at, or two other considerations, are the energy of the collision. So just because a molecule collides with another doesn't mean a reaction is going to happen. It has to collide with enough energy to rearrange the bonds, exchange electrons, and do whatever else it has to do to create products from reactants. And the orientation of the colliding molecules also matters. If a molecule collides with another and the orientation of those molecules is not correct, they will essentially just bounce off of each other because the reaction won't be able to occur because the right bonds and electrons are not lined up correctly. So unless they're lined up correctly, a reaction won't occur, and if there isn't enough energy as the molecules collide, then a reaction won't happen. So again, here's the concentration. More molecules, higher concentration means more potential collisions, which means a faster reaction rate. So in general, doubling the number of collisions should double the rate of the reaction. Now, if we look at temperature, okay, so we've seen tables like this before where we have several different experiments and we've changed the concentrations of reactants and products. But in this case, our reactants are not changing concentration. They're both remaining at 0.1 and 0.2 molar respectively. The only thing changing here is the temperature. Okay, so as the temperature is changing, notice that the rate of the reaction is changing. That makes sense because as the temperature increases, we are increasing the kinetic energy of the molecules, which gives them overall more energy. More energy means that when they do collide, there's a good chance that more of those molecules are going to have enough energy to make a reaction occur, and that will increase the rate of reaction because the number of effective collisions or collisions that result in a reaction are increasing. Now, if the rate of a reaction increases, the rate constant must also change. Now, if we look at the rate law again, we can see why this would be the case. So this is going to be, I'm just going to call it A and B for reactants and products. So I'll call this one A for the ester and B for water. So if the things that are remaining the same are the reactants, so those remain the same, we observe that the rate is changing, and the only thing on the right-hand side of the equation that can result in a change in the rate is if the rate constant is changing. Okay, so temperature is going to affect the rate constant, and we can see how that occurs in this reaction by just looking at this graph here. So it's not a linear change, it's an exponential type change. The shape of that doesn't really matter, but this is just showing you that the rate constant K is changing with temperature. So let's talk a little bit more about collision theory. I talked just briefly about it in the last slide. So in order for a reaction to occur, particles must collide. If they don't collide, then a reaction can't occur. And the greater the frequency of those collisions, the higher the reaction rate. That makes sense, right? More things colliding, more things converting from reactant to products at a faster rate. So the rate is proportional to the collisions per second, which is proportional to the number of molecules in a reaction that are colliding in an appropriate manner in order for a reaction to occur. So normally when a collision occurs, it's only between two particles or two molecules, because it's unlikely that three molecules will collide at exactly the same time. You can sort of prove this to yourself at home if you have three tennis balls or three other objects that are the same, and you try to throw them up in the air and make them all hit each other at the same time. It's pretty much impossible to do. Two is obviously easy because you just got to throw them at each other, but three is not going to happen very often, if at all. Right? You can get two to collide at the same time, then that third one will probably come in a little bit later. So only two particles may react at one time, and there are a few factors that determine whether a reaction will even occur. So we talked about just briefly molecular orientation in the last slide, where they must collide in the right orientation, otherwise a reaction won't occur. They have to have enough energy, the molecules, in order to react. And as we'll see and talk about, the reaction has what's called an activation energy, which is an energy barrier, an energy that the molecules must reach in order for a reaction to occur. So we'll see that in a minute, what it looks like, and it'll make more sense when I get there. Okay, so again, not all collisions are what are called effective collisions, right? So they have to be in the right orientation, and they must be at an energy that will allow the reaction to occur. So when two molecules react, you can picture two reactant molecules reacting to create two product molecules. At some point in time, for just a fraction of a second, as the reactants are colliding and coming together, they form what is called an activated complex or a transition state. And this is just essentially those two reactant molecules together as they are rearranging their bonds, and it forms during an effective collision. So here's what it would look like if we had two reactants and creating two products. So we have one chlorine and then an NOCl, nicely color-coded so you can follow the molecules and the atoms. So if we had an effective collision, which is represented by the top figure, before the collision we have separate chlorine and NOCl. As they collide, we have what is called the activated complex or the transition state. And as that activated complex is present, electrons and bonds are being rearranged so that when they finish reacting, we end up with products, right? Our Cl2 and NO. Now the second figure shows a collision that is not effective. And the reason for this one seems that the orientation is not correct. So we need to have the two chlorine molecules, right? We'll look at the top one again. So those two chlorine molecules have to be oriented in such a way where they will collide with each other in order for the reaction to occur. So in the bottom figure, they're not lined up. So we have a chlorine reacting with a nitrogen. That's not the correct orientation. So even if they have enough energy for a reaction to occur, since they're not oriented correctly, then they essentially just bounce off each other and we still end up with the reactants in this case. So this was not an effective collision because the reactants did not produce products. So let's talk about how temperature affects the rate of a reaction. It does it in a couple ways. So first of all, what temperature does is it increases the kinetic energy of all the molecules in a particular reaction. So it's making them move faster, it's giving them more energy. So when they do collide, there will be more molecules with enough energy to allow a reaction to occur. Okay, so the more molecules will have enough energy to form an effective collision. Now what it also does, since everything is moving faster, is it increases the number of overall collisions. Now we talked a bit about activation energy, which is the minimum energy of molecular collisions required to break the bonds in the reactants, leading to the formation of products. So in a couple of slides I'll show you that in a pictorial form so you get an idea of what it really means. But again, that's the energy that is required for a reaction to occur. So when they do collide, they have to have what is called the activation energy, or enough energy to overcome an energy barrier for that reaction to actually occur. So these factors, the temperature and activation energy, are incorporated into a rate constant, K, by what is called the Arrhenius equation. And that is shown here. So there's the Arrhenius equation. We have a rate constant, activation energy, and temperature. So another useful form of the Arrhenius equation is the log form, which is at the bottom, and as with other equations we've seen in both this chapter and chapter 11, it ends up being in the form of a straight line. So our natural log of K is the Y, activation energy over the gas constant is M, temperature is X, and the natural log of A is the Y-intercept. We'll come back to this a little bit later, but I want to expand the conversation on temperature a little bit more. So I want to show you what a graphical representation of temperature and kinetic energy would look like. So we have two graphs here, a purple line and a green line. The purple line represents a reaction at a low temperature, whereas the green line represents a reaction at a higher temperature. Now, as you can see, we also have on this graph an activation energy. So this dotted line is showing us how much energy is required for a reaction to occur. And the areas under each of these curves, the purple and the green curve, give us an idea of how many molecules have a specific amount of energy. So for the purple line, most of the molecules have this much energy here. So at the top of that curve, most of the molecules have that much energy. For the green curve, increased temperature means more molecules have more energy. So most of the molecules, on average, have more energy underneath the green line. Now the shaded portion of each of these shows how many molecules have enough energy to react or to overcome the activation energy. So notice with the purple line, the lower temperature, we have fewer molecules compared to the green line that have enough energy to react. So this is showing you that because we have more molecules that have enough energy at higher temperatures, more molecules that have enough energy to overcome the activation energy, more of those molecules will have an effective collision. So that would mean that the rate of the reaction would be faster at a higher temperature. So let me break it down a little bit and show you how this would proceed. So what we see here is a potential energy diagram. So here we have the reactants have a specific amount of energy, the products have a specific amount of energy, and this curve, or the top of this curve, represents the activation energy, or the energy required for a reaction to occur. So when the molecules react, or when they collide, they need to collide with this much energy here in order for a reaction to occur. So initially we only have reactants. So here's our reactant 1, here's our reactant 2, and as they come together, as they collide, what happens is we get this transition state or activated complex. So as you can see at the top, we have bonds forming, we have bonds breaking, but the activated complex is both of those molecules together for a fraction of a second as this rearrangement occurs, as some bonds are breaking and some bonds are forming. All right, so again, here is our activation energy. So the molecules have to have that much energy in order for a reaction to occur. If they have less energy than that, they'll bounce off each other and a reaction will not occur. So after the molecules react, they've gone through the activated complex, they've exchanged their electrons, they've created bonds and broken bonds. What we end up with is our two products. So now we have two NOs and one Cl. Okay, we have the new bond that was formed and the bonds that no longer are there because those are the ones that were broken. Now, not all activation energies are large. Some of them are much smaller. If you recall from the beginning of this chapter, we talked about pollution from fossil fuels and its effect on ozone. So this is a reaction from that again. So this is looking at how ozone reacts with the nitrous oxide that is formed from fossil fuels, from the burning of fuel in our cars or our industries, which results in that ozone breaking down to oxygen and NO2. And the NO2 is the brown gas that you may see on smoggy days in big cities. So we have another potential energy diagram here, but what I want you to notice is the activation energy. It's quite small in this case. So what that would mean is that the reactant molecules, the NO and the O3, since they don't have a large energy barrier to overcome in order to react, most of those molecules are going to have enough energy. They only need 10.5 kilojoules per mole. Now, I know that doesn't mean much in terms of a number, but you'll be able to compare it to the number on the next slide. So you can use it as a relative measure, if nothing else. So just know that this is a very small activation energy. If most of the molecules have enough energy to react, then that reaction will proceed very fast. Lots of molecules are able to have an effective collision, so they can easily produce products. Okay, so this is the takeaway from this slide. Lower activation energy, large rate constant, fast reaction. Now, if we look at the same reaction, but in reverse, okay, so we're looking at it in reverse, now we have a much larger activation energy. So the activation energy for the reverse reaction is 210 kilojoules per mole. So compare that to 10.5 kilojoules per mole. It's about 20 times greater. So what that would mean in terms of the energy of the molecules is that there would be far fewer molecules that would have enough energy to form an effective collision. So the reverse reaction, going from O2 and NO2 to NO and ozone, is going to be a slower reaction because fewer molecules have enough energy to overcome that energy barrier. So in the next chapter, chapter 14, we'll talk more about forward and reverse reactions, and it will become more common because most reactions actually are reversible, meaning they can go forward and they can also go backwards. Okay, so now let's get back to the Arrhenius equation and how we can use it to determine activation energies. So what we do is we would run an experiment at different temperatures. So there's our temperature on the x-axis. We would measure the rate constant of each of those reactions. And then if we were to plot our Arrhenius equation, again, this is in the form of a straight line. Okay, we have, again, that's x, natural log of k is our y-axis. The slope, activation energy over the gas constant, and natural log of A as the y-intercept. So what we get from this, we would look mostly at the slope because we're probably interested in the activation energy. So in order to separate the activation energy in the slope, right, notice the slope is minus EA over R. We just want EA, or the activation energy. We would just multiply the slope by negative R. Okay, so if we were to do this, here's what it would look like, right? So this is 4 experiments. We measured the rate constant, and the rate constant is changing as the temperature is increasing. Okay, we have a specific reaction we're looking at. Now, if we wanted to determine the activation energy, the next slide shows the steps that would be involved. So first, we would make a column of natural log of K data, right? We already have K, just take the natural log of it, make another column. Make a column of 1 over T in Kelvin, and then we would plot natural log of K on the y-axis versus temperature on the y-axis, and then calculate the slope. Once we know the slope, we can easily figure out the activation energy. Now we can also do this without graphing, or if you want to call it just mathematically. I know graphing is also mathematical, but we'll just separate that, calling it graphing. We'll call this the mathematical determination of the activation energy. So if we start with the Arrhenius equation in the form of a straight line, and we want to consider two different temperatures, T1 and T2, we would also have two different rate constants. And if we subtract those two equations, we end up with this equation right here. And we can use that equation also to determine the activation energy. So the last slide I have here, we'll just go over an example of how we would do that determination mathematically. Okay, so here's our data again, and we know that we're going to be using the equation shown here as well. Now for this, we have 3 sets of data. You can choose any 2 you want. You should get a very similar answer no matter what you choose, but I'm just going to choose the first experiment and the second experiment. So if we use experiment 1 and 2, we can substitute those values into the equation. So we're going to have natural log of K1, 2.9 times 10 to the minus 3 seconds to the minus 1, divided by 6.1 times 10 to the minus 2 seconds to the minus 1, equals EA over 8.314 joules per mole Kelvin. And it's going to be multiplied by 1 over 450 Kelvin minus 1 over 400 Kelvin. Okay, so now I'm just going to consolidate what I can. So this, if I do that, that equals minus 3.046 equals EA over 8.314 joules per mole Kelvin multiplied by this, which ends up being minus 2.78 times 10 to the minus 4 Kelvin. Okay, now if I just rearrange the equation, EA is going to equal minus 3.046 multiplied by 8.314 joules per mole Kelvin divided by minus 2.78 times 10 to the minus 4 Kelvin. And kelvins are going to cancel out. We're going to be left with joules per mole. So EA, activation energy, is going to equal 91,095 joules per mole. Now we only have 2 significant figures, as we can see up here for our rate constants. So we can just turn this into a kilojoules per mole, and that would be 91 kilojoules per mole. Okay, so that's all I have for this. I hope it all makes sense. If it doesn't, feel free to contact me either by email or by visiting my Zoom office hours.